Hello, everybody. I'm Linyi, and I just graduated from UIUC with a PhD degree. So thank you for this great opportunity to introduce our work in certifying trustworthy deep learning systems at scale. So let me start. So as we all know, deep learning systems are now reforming our lives. So like in many applications, and we also know that there are many threats of trustworthiness in deep learning systems, like in robustness threat, fairness threat, toxicity threat, and privacy threat. So they widely exist, and like in many applications, they have, it has been shown that it can cause serious consequences, such as fatal traffic accidents, and also most recently in Amazon, there is an Amazon drone that caused a fire spreading 25 acres, and the root cause is investigated and then found to be some defect in the neural network controllers. So actually, these threats can be converted to actual attacks. Like we have done an attack that can make two face images to be quite different, but they can be identified as the same person with a very high success rate. It can be directly used to attack commercial APIs without any access to the internal model. So due to all these various prevalent and dangerous threats of trustworthiness, the trustworthiness in deep learning has now raised serious social concerns. And then to mitigate these concerns, we need to have a rigorous and accurate evaluation of deep learning trustworthiness. To evaluate so, actually, the whole pipeline of current research is that we first identify several trustworthy properties, and such as robustness, such as fairness and numerical reliability, and then define the expected input and output behaviors by looking at these trustworthy properties. So one example that we are actually intensively working on is the adversarial robustness. For instance, in adversarial robustness, we care about whether small perturbation can make the neural network to give wrong predictions. Like here, suppose we have a finite data set of several samples, and then to check the trustworthiness in terms of robustness, what we are doing is to check whether for any small perturbations, the output will always be correct. So to evaluate so, actually, there are two main branches of approaches: empirical approach and certified approach. So empirical approach tries to find such adversarial example to mislead the model. And then suppose we have an empirical approach that can deteriorate the model's accuracy from 90% to 60%. Actually, we don't know to much degree the model is trustworthy, because there may always exist a future attack that can further deteriorate the accuracy. So now comes the value of certified approach. If you can certify that for 55%, the model is always correct, then we can shrink the degree of trustworthiness to within 55 and 60 degree under this given distribution. So hence, we view certified approach as a way of reliable evaluation of models' trustworthiness. And we actually cares about two main properties of certified approaches: tightness and scalability. So tightness means that if the model is really robust, we hope that we can have a tight bound and we can actually certify it. And then scalability means that we hope to make it scale up, as previous speakers have said, maybe to support LLMs. So our research works intensively in this certifying trustworthiness field, and we are actually building whole layers of architectures to certifying large-scale deep learning models. First, we build certified approach to the state of the art by making it more scalable and by making it tighter. And then at the second layer, we then deploy training approaches to steer the model to be more certification friendly. And then we apply that in applications, and then we build the whole infrastructure for it. So in this talk, I will introduce two work. The first work tightens the certification, and the second work generalizes the certification for robustness to more trustworthy properties, here, semantic robustness. So let me first introduce the first approach, DSRS. So DSRS is actually certifying the adverse robustness against a very classical perturbation model, which is p-norm constraint perturbations. So here, we are trying to test whether the model is robust, whether the classification model is robust given small perturbations. So we assume the attacker can craft any perturbations. So, and then for this direct model, actually there is a long history of research in terms of white box verification. But here, we took a different approach, like to certify a large radius, not large perturbation radius, we took the approach of randomized smoothing. So randomized smoothing directly tackles the inherent challenge of white box certification by changing the inference protocol. Like in normal white box certification, we just certify a system that takes the input and directly through the neural network to get the output, which is proving to be quite challenging, like and be hard to be certified. So we take randomized smoothing, which is not proposed by our group, but we leverage it. Like it is a post-processing inference protocol that can construct large models based on neural networks, but make it easier to be certified. So what randomized smoothing looks like. So here is a high-level overview. Randomized smoothing composed of two steps. First, we train a deep neural network, which we call base classifier, under some noise. Like we add Gaussian noise, for example, as the augmentation to train the classifier. Then, based on this base classifier, we smooth it to build a new pseudo classifier, which we call smooth classifier, such that this smooth classifier, each time for each input, it adds several noise, and then take the majority voting and choose the most probable prediction by this base classifier. So in deployment, we use this smooth classifier. So here's the illustration. So in randomized smoothing, suppose we have a cat image. Then we add several Gaussian noise to augment it. And then suppose for this augmented cat image, we have 80% that base classifier predicts cat and 50% to predict dog. Then we take cat at the final prediction. So the purpose of using randomized smoothing is that if we slightly shift the center of the distribution, it can change the outcome probability, but if the gap between top prediction and run-up prediction's probability is large, then it cannot, any small perturbation cannot change the rank of the probability of the predictions, so that we could obtain robustness against adversarial perturbations. So actually, based on this intuition, there is a very neat result in 2019 that we only need the top class probability and the runner-up class probability, and then the noise variance to get a certified radius within which any perturbation cannot change the prediction. So as we can see, using this approach and this closed form equation, we don't need any knowledge about the model architecture, or we don't need some classical white box certification methods to propagate some intervals or propagate some polytopes. So it's quite scalable. But can randomized smoothing actually certify large-scale deep learning systems? However, it still can't. The reason is that there is some theoretical work that shows that randomized smoothing cannot certify high L-infinite robustness for high-dimensional input. So this may be too formal, this statement, but it can change to equivalent meaning that for perturbations whose L2 radius or Euclidean magnitude is a constant, then if we increase the input dimension, the actual perturbations magnitude is actually shrinking. But the randomized smoothing can only certify a constant Euclidean radius. So it means that for very high dimensional data, the actual radius that randomized smoothing can certify is almost trivial. And our research actually tries to solve this problem. So how do we solve it? We found that all this randomized smoothing certification work only leverages the probabilities of the smooth classifiers prediction under one distribution. But actually, since the base classifier are trained by us, so we're actually able to leverage more information to tighten the certification of randomized smoothing. So then it comes to our approach, which is a bit directive, which is a bit intuitive, which is that actually we sample the noise under two distributions. One is the distribution that we conduct the smooth classifier, and another distribution is what we deliberately chosen to characterize more properties of the base classifier. So it is shown here in the blue box where we sample two probabilities, PA and QA, from two distributions, P and Q. By leveraging the information from two distributions, we can actually view the certification process as solving a constraint optimization with another constraint. So with this new constraint, we can tighten the solved objective to get a tighter certification. So it seems like a small change, but as our theory showed, this small change can have a drastic improvement. Actually, because this small change introduces a larger level of degree of freedom, like the chosen of another distribution Q. So by choosing a good Q distribution, we can actually prove that such certification with another constraint can be optimal, which means that the Euclidean certified radius with another distribution can actually be scaling up with respect to the input dimension of the problem. So now we can see with DSRS, randomized smoothing can actually scaling up to certify current large models that has high dimensional input. So here are some details about how to solve with the additional constraints, but I'll skip it for now. So we then implement DSRS in the real world, and we found that actually, like randomized smoothing, they can certify large models on ImageNet, which is not large language model scale, but also has millions of parameters. And we see that with DSRS, we can gain a significant improvement of the certified radius. Like on ImageNet, we can improve the certified radius by 7% to 10%. And we can see on larger models and larger data sets, we can see a larger gain. So as a quick summary, DSRS is the tightest certification for large models so far based on randomized smoothing. And it can circumvent the long-standing theoretical barrier of randomized smoothing or a group of black box certification methods by scaling up to high dimensional inputs. And it actually represents a path for certifying large models, which is to leverage more information, and which can also be viewed as have a finer-grained abstraction of the model. Have a fine-grained abstraction is actually a general methodology for certifying models, like in informal verification. But for randomized smoothing-based certification, people are ignoring it. They are just leveraging some small statistics or a limited quantity of statistics, but not leveraging more information for randomized smoothing itself. So this is our first work that can tighten the certification. And it is actually just one stage of our whole pipeline of building certified robustness networks against constraint perturbations. And then besides tightening the certification, we also need to generalize the certification to real-world specifications. So now it comes to our second work. In our second work, we generalize the certification methods and make it available for certifying natural geometric transformations. What are natural geometric transformations? They are like brightness change, they are like contrast change, and they are like some transformations that commonly happens in real-world images. So such geometric transformations are actually widely exist, and they have been shown to be able to attack the deep learning systems with high success rate. So natural question is how to build certifiably robust deep learning systems against such semantic transformations. So our TSS can achieve this goal. So in TSS, we tackle the previous work's problem of too loose, too slow, and too specific. So we built a framework that is tight, is scalable, and is general. So in TSS, our threat model, or to say the attacker's ability, is that it can choose some transformation, and then choose arbitrary hyperparameter to execute the transformation, and then input the transformed input to the classifier. Like in rotation, it corresponds to an attacker that can arbitrarily choose a rotation angle to execute on the input. So actually, for such transformation, the certification is quite challenging due to three main challenges. First is that with an arbitrarily chosen hyperparameter, there are actually infinite number of possible inputs because the attacker can actually choose any real-valued parameter. So we cannot certify it by just enumerating all possible inputs. And then such certification is also challenging because we cannot leverage existing LP-bounded or noise perturbation certification, because such transformation can usually incur a large and visible difference between the original input and the transformed input. So it seems like a quite visible perturbation, but doesn't change the latent semantic meaning. And then such transformations can also trigger the interpolation effect, like for common images, like if you exert some rotation or scaling, we usually use bilinear interpolation or other types of interpolation mechanisms to get the final output. So the certification method also needs to take this into consideration. And TSS is actually a framework that can solve all these three challenges. In TSS, actually, it composed of two main components. The first component is TSSR. Like for certain family of transformations, we can generalize randomized smoothing to provide certification for it. And then for those transformations that cannot support randomized smoothing, we leverage standard robustness certification and integrate space partitioning to rigorously upper bound the interpolation error so that we can build certification for it. Like first, I'll introduce TSSR. So TSSR is a generalization of randomized smoothing. So how do we generalize randomized smoothing? So we'll look back to the randomized smoothing's classical notion, which is that we add noise directly to the input. And here, to defend against semantic transformations, we change the noising mechanism to be sampling noise of the hyperparameter of the given transformation. Like here, previously we sampled the noise epsilon and directly added it to the input. Now we sample noise of the hyperparameter of the transformation and then add it to compute the majority voting. Suppose we are certifying the model's robustness against brightness change. Now, with our generalized randomized smoothing, we sample the epsilon, which is the brightness change hyperparameter, and it will induce several brightness change cats. And then we apply majority voting over them to get the final prediction. And in this way, we're able to solve the certification problem for a group of transformations. However, this is not the end of the story, because we found to provide certification with generalized randomized smoothing, the transformation itself must satisfy some conditions. Like the condition that we highlight here is that for such transformations that support generalized randomized smoothing, they must have some overlap supports between the transformed input and the original input under some distribution. However, this condition is hard to be satisfied by some transformations, like rotation and scaling, are not satisfying this condition due to the interpolation. So how to support the certification for these transformations? Actually, we first categorize the certifications into the transformations into two groups. For those that can support generalized randomized smoothing, we call them resolvable transformations. And for those we cannot leverage generalized randomized smoothing, like what I mentioned, rotation and scaling, we call them differentially resolvable transformations. And to solve it, we leverage two great findings for these differentially resolvable transformations. The first finding is that compared to noise perturbations, such transformation perturbations are usually lying in low dimension. Like for rotation, there are just one degree of freedom, the rotation angle, and then for scaling, it's the scaling ratio. So by leveraging this low dimensionality feature, it is feasible to conduct an epsilon cover of the whole space of transformations, the whole space of transformation parameters. And then with a relatively intense cover of the whole transformation parameter space, we can then compute the Lipschitz constant of the transformation with respect to the input. So in this way, we can bound what is the maximal violation of any transformed input with respect to the nearest element in the epsilon cover. In this way, we're able to reduce the problem of semantic transformation certification to classical LP-bounded or Euclidean perturbation certification by checking whether for any elements in the epsilon cover, it can have a Euclidean robust radius larger than epsilon times L. And then in this work, we leverage some samplings and data-dependent Lipschitz computation methods to actually figure out a computable bound of the Lipschitz constant, and then leverage it. By leveraging it, we're able to scale up the certification for semantic transformations to an ImageNet level. Here are the results. As we can see, we can achieve 70% guaranteed accuracy on ImageNet for brightness change. And they can also, and a more amazing result is that actually for models that are certifiably robust to sound transformations, we found they are also able to generalize, which means that for unseen transformations, like the transformations in Cipher 10C and ImageNet C, including some blurring, including some rain or snow effects, the certified models are still more robust than other non-certified models. So this means that by making the model certifiable, it actually aligns the model with our humans' expectation more. So TSS is the first large-scale certified defense against semantic transformations, and it also induces several subsequent work that can generalize the TSS or transformation-specific smoothing idea to more modalities. Like we can also leverage it to certify point cloud models. We can also leverage it to certify the perception model in the perception module in robotics, and we can also certify it against some unknown transformations or natural transformations by learning the transformation with a mapping module. So, and then by leveraging all these ideas from image domain robustness, we can generalize it to a broader group of trustworthy properties and broader domains. So after leveraging all, these two works, actually it's just a showcase of our efforts that have unlocked the trustworthiness certification for large deep learning systems and our work for enhancing the certified trustworthiness. And now let's look ahead. So the core goal of our research is certifying trustworthy deep learning systems. So a core research problem is that with all these techniques, how far have we already gone? So actually, despite our effort on this, there are still 3 key challenges in building certifiably trustworthy deep learning systems. The first challenge is tightness. So despite our effort, we found that for large models, the certification is still quite loose. Like for MNIST models, we can actually prove its robustness for 94% of the test input. But on ImageNet, with a reasonably large perturbation radius, we can only prove the robustness of just up to 30%. So, and also another side effect of certification is that to make the model certifiable, we're actually sacrificing much of its accuracy. Like on MNIST, the certified model still have high accuracy of 96%, but on ImageNet, to make it certifiable, the accuracy has dropped from 74% to lower than 50%. So for practitioners or actual users, this drop is quite large and cannot be tolerated. So then we look into the problem of why this happens. So our idea of the root cause is that to make the model certifiable, we're actually steering the model itself to fit the certification method. Such fitting is usually in the form of propagating some symbolic intervals, or in randomized smoothing is by making the model to tolerate large unrealistic noise. So with such fitting, we can obtain some degree of certifiability, but as a severe side effect is that such fitting makes the model to have bad accuracy. So, and we believe such problem is actually intrinsic to this paradigm of building certifiably trustworthy models. So how to fit them? So our idea is to revert the whole paradigm of first decide on architecture, then fit it for certification method. Instead, we should incorporate the certification methodology from the first place, which means that we should choose some learning paradigm or architecture that is intrinsically interpretable and certifiable. So our ongoing work has investigated such methodology, and we propose a learning paradigm that integrates some metacognition and the neurosymbolic method by building a learning pipeline composed of learning and reasoning component. The learning part are a group of classifiers that identify some properties, and then we feed the specific classifiers output probabilities to a reasoning pipeline, which is built up on the probabilistic circuit. In this way, we can build a certifiable learning pipeline from the first place, and then we feed this whole pipeline to the downstream tasks, and then we can achieve a significantly higher certifiability. This is an ongoing work, so I didn't introduce much details, but please stay tuned for our final result and publication. And then, despite the tightness certification, or the tightness challenge, another challenge is on the scalability. In scalability, a natural question is that we can already certify ImageNet scale models, but can we certify LLMs? Unfortunately, the answer at the current point is no. It is because of several key challenges, like the high inference cost of LLMs and the highly nonlinear in the attention module, which is not friendly for certification, and the uncertain sampling procedure. But a good news is that we're investigating them, and then we found it is not totally infeasible. Actually, the challenges in certifying LLMs can be solved in a divide and conquer way. Like we can build a high quality data to shrink the model size. We can also build more certifiable architectures with neurosymbolic methods, and also we can change the sampling procedure in the LLMs to have some probable guarantees. In this way, we have made some promising progress in certifying large language models. Currently, we can certify the large language models up to 2 billion parameters, but maybe there's still a long way to go compared to the normal model size of Llama, which is around 34 billion. But we are working on that. And then the last challenge of certifying large models is the generalizability. The community has investigated heavily on robustness, and we have extended to some other properties. But can we actually provide an end-to-end certification for concrete safety-critical applications? Actually, I think for this direction, there are less work, like how to certify some end-to-end applications like UAVs, drones, autonomous driving, and robotics. So we think to build such certification, we need to have an automated pipeline that can extract the specification and extract the word model, and then directly integrates them to be a certification pipeline. So in summary, the certifiable machine learning, this whole field, can be viewed to be equal to controllable AI, which coincides with the goal of metacognitive and neurosymbolic methods, which is to answer the question of how to learn while conforming to specifications or safety constraints. So all the works that I have discussed are aiming for this ultimate research problem, and we will also we will proceed our research to solve this ultimate research problem to give a controllable AI system. So as a final conclusion, we believe AI revolution is at the corner, but without certification, humans are not ready. So it's our responsibility to equip AI with certification and to make AI controllable so humans can embrace AI revolution. So here are some references, and thanks to my collaborators and advisors. So I'll stop here. Any questions are welcome.
Okay, let's thank the speaker.